A chemical reaction occurs when reactants transform into entirely new products, characterized by distinct chemical properties and identities. This process can be identified through macroscopic evidence, such as changes in state, color variations, gas evolution, or temperature fluctuations. These transformations are omnipresent in daily life, occurring during common phenomena like the spoiling of milk, the rusting of iron, cooking, and cellular respiration. Chemical reactions are represented through word equations or symbolic skeletal equations, which must be balanced to satisfy the law of conservation of mass. Balancing is achieved using a systematic hit-and-trial method where whole number coefficients are added in front of formulas without altering their subscripts. A complete equation includes physical state symbols and explicitly notes specific reaction conditions, such as temperature, pressure, or catalysts, along the reaction arrow. Chemical reactions are broadly classified into 5 distinct categories based on how atoms and ions interact. These include combination reactions that synthesize a single product, decomposition reactions that break a compound down using energy, and displacement reactions driven by elemental reactivity. Additionally, double displacement reactions exchange ions to frequently form precipitates, while redox reactions simultaneously transfer electrons through paired oxidation and reduction processes. Corrosion and rancidity are 2 damaging oxidation processes commonly encountered in everyday life. Corrosion progressively degrades environmental metals like iron and copper through destructive electrochemical reactions, though it can be mitigated via protective methods like galvanization and painting. Similarly, rancidity develops when atmospheric oxygen oxidizes fats and oils in food, a breakdown that manufacturers prevent using antioxidants, nitrogen flushing, and airtight packaging. The 5 primary chemical reaction types, combination, decomposition, displacement, double displacement, and redox, each follow highly predictable structural and elemental patterns. While combination reactions typically release energy as exothermic processes, decomposition reactions break bonds by absorbing energy endothermically. Recognizing these specific reaction classifications and electron transfer mechanisms allows chemists to accurately anticipate resulting products and environmental temperature variations. This glossary defines core chemical terms, distinguishing initial reactants from the newly generated products represented within balanced chemical equations. It outlines critical energetic concepts, defining exothermic and endothermic reactions by their respective heat release or absorption, alongside the role of unaltered catalysts and insoluble precipitates. Finally, it contrasts the chemical mechanisms of oxidation and reduction while addressing the environmental degradation processes of metal corrosion and lipid rancidity. This reference text details specific real-world examples for each of the 5 core chemical reaction classifications. It pairs combination processes like the burning of magnesium with diverse thermal, electrical, and photolytic decomposition reactions. Furthermore, it illustrates single and double displacement behaviors using metal salt solutions, alongside foundational redox reactions such as the reduction of copper oxide by hydrogen.